Okay, looking at half-life example problem set number 2. As previously stated before, I would copy these example problems down your notes, leave plenty of space before you copy them down so you have a good record of them later on in your math careers. And we're going to be using the same formulas that we did before. So we're going to use P is equal to P naught E to the RT. I'm going to refer to it as PERT. Because it looks like PERT. So our first steps are always to find our R. So start with P is equal to P naught E to the RT power. Okay, it says the half-life of carbon-14 is 6,000 years. So half-life is half the original amount, and it's 6,000 years. P naughts will cancel like they did before. And so we have this equation right here. 1/2 is equal to E to the 6,000 R. Okay, so we're going to natural log both sides to solve for R. So we get natural log of 1/2 is equal to 6,000 R, natural log of E. Natural log of E goes to 1. And we're going to divide both sides by 6,000. So natural log of 0.5 divided by 6,000. And it's that same number from the previous example problems, negative 1.1552 times 10 to the negative 4. Okay, now we want to know how much of this sample will remain after 15,000 years. Okay, so we're looking for P, the final amount. Your initial amount is 15 grams. And we're going to plug in 1,500 years. Okay, so when we plug this in our calculator, we're going to take this number and multiply it by 1,500. We're going to do second natural log, pulls up the E, and we're going to use answer. And then we're going to multiply it by 15. Okay, so you get 12.6134. So that's how many grams will remain after 1,500 years. Okay, a fossil sample now contains 60 milligrams of carbon-14. There were originally 133 milligrams of carbon-14 in the sample. If the half-life of carbon is carbon-14 is 5,730 years, find the approximate age of the fossil. Same steps as before. P is equal to P naught E to the RT. We're going to do our half-life. So half the initial amount. We're going to solve for R. Now the half-life of carbon-14 is 5730. P naughts will cancel. So we get 1/2 is equal to E to the 5730 R. So to solve for R, we're going to natural log both sides like we did before. Natural log of E is 1. And we're going to divide both sides by 5730. And you get that number. So R is equal to negative 1.2096, or 97, let's do 97, times 10 to the negative 4. Now, from there, we're going to use our formula once again. Now we want to find out how old the fossil is, so we're going to be looking for T. So it says it now contains 60 milligrams. There were originally 133 milligrams. Your R is a negative 1.2097 times 10 to the negative 4, and we're solving for T. So we have that function over there. So our first step is to divide by 133. So 60 divided by 133. You can leave it as a fraction if that's better, or you can do it as a decimal. Just make sure you go plenty of decimal places. Okay. Now, To solve for t in the exponent, you're going to natural log both sides. And natural log of e goes to 1, as we did before. So to solve for t, you're going to take natural log, so natural log of 60 over 133, and we're going to divide it by negative 1.2097. Remember to put e in the calculator times 10. You're going to do second comma, okay? So it's 6,580 years old. Let's go 2 decimal places. Okay, so they actually do use this for calculating the age of fossils and organisms that are buried in rock. So these are some applications of exponential functions. We looked at compounded interest and half-life. So hopefully this was able to put some stuff in perspective for you. If you have any questions, please feel free to reach out. Have a good afternoon.